Okay, we've already said the normal distribution for the distribution of means utilizes this formula, and we're going to use this video to compare working with the t-distribution and using this formula and look at the difference between the two. Now, please remember, for the normal, we have to know the standard deviation of the population. Here, we're using the standard deviation of the sample. The t-distribution, the sample of means is normally distributed. The mean of this set of sample means is equal to the population mean. In other words, what we said earlier, the mean equals the mean equals the mean, so that never changes. And we know that the standard deviation of the standard deviation of the sample mean is approximately normal, or is approximately this, whereas the standard deviation for the normal is this, right? But when we're working with the t, it just becomes the standard deviation of the sample mean. So it's the standard deviation of the sample divided by the square root of n, versus the normal was the standard deviation of the population divided by the square root of n. So here's our scenario. A college's data about the incoming freshmen indicates the mean of their high school GPAs was 3.4. So they're telling us, okay, our mean is 3.4. The students are randomly assigned to freshman writing seminars in groups of 25. Assume that the GPA, so it's groups of 25. They're telling us it follows the normal distribution, which is important because our sample size is less than 30. What's the probability that the mean of the student is less than 3.3? So they want to know what's the probability that X bar is less than 3.3 given the standard deviation of the population is known as 0.35. So we know the standard deviation of the population, so we can use Z. So we're going to have, what we're looking for in this case is the probability that Z is less than 3.3 minus population mean of 3.4 divided by standard deviation 0.35 divided by the square root of our sample size is 25. And I should be drawing my picture. My picture would have looked something like this. We know that the mean is 3.4. And we want to know the probability of having a X bar of 3.3. And we said less, so we're shading this way. Now, a couple things about this. We can go to a stat test, Z test. Stat test, Z test. Our mean was 3.4. Not 3.5, 3.4. Our standard deviation was 0.35. Our X bar was 3.3, and our N happened to be 25. And we go calculate, and we end up getting a Z score of negative 1.4. And remember, they're very important that we write down our Z score. So the probability that Z is less than negative 1.4285 equals 0.0765. So about a 7.65% chance of that happening, okay? And of course, we could have done this as a norm CDF, but the key thing is make sure you're calculating the Z score. All right, so let's compare that. What's the probability that the mean GPA of the group is less than 3, given that the standard deviation of the sample is 0.35? I want to change this. This should have said 3.3. This way we're using the exact same X bar. So this was for the normal. So now we're going to look and do the same thing, but we're going to work and use it using a t-distribution. So using the t-distribution, my curve is still centered at 3.4. We have an x bar of 3.3. So really I have exactly the exact same picture. And you don't have to label normal t, but I'm just doing that for ease of this. And we're looking for the probability that t is less than 3.3 minus 3.4 over 0.35 divided by the square root of 25. Now, in this case, my sample size isn't large enough, but they told me that the underlying distribution was normal. And since they had told me in the problem the underlying distribution is normal, I can go ahead and do this. Otherwise, I could not. To use the t, the underlying distribution has to be normal, or my sample size has to be 30 or larger. So we're going to look at doing this two ways. So stat, test, and I can go to a t-test, press enter. Mean is 3.4, standard deviation is 3.3. I mean, the x bar is 3.3. Our standard deviation is 0.35. N is 25. And the probability that t is less than negative 1.4285 equals 0.0830. Now, what's important about this is the formula looks the same. The number of standard deviations is the same, but our probability changed. So our probability changed, and we have a slightly more probability of this happening because we have more area in the tails, and that makes sense. All right, so this was about 7.6%. This is about 8.3%. I do want to go one other place on the calculator because I want you to know that this exists because you'll need this. Let's go to second vars, and let's go to TCDF. Well, we're shading to negative infinity, and we have an upper bound of negative 1.4285. And my degrees of freedom would be 25 minus 1, because it's n minus 1. And there's that 0.083 again, all right? So you can do this as a TCDF, and every now and then you'll have to do it because they'll give you a T statistic. If they give you a T statistic, you're going to have to use a TCDF, all right? If they give you a T statistic, you'll have to use a TCDF. But if they give you X bar and the standard deviation, you can go directly to stats test, t-test. All right, so continuing on, scenario 2. Assume that the duration of human pregnancies can be described as a normal. So once again, they're telling us the underlying is normal with a mean of 266. Suppose a certain obstetrician is currently providing prenatal care to 60 women, so N is 60. What's the probability that the mean of these patients' pregnancies will be less than 260? So in other words, they're asking about the mean. So this means this is an X bar if the standard deviation of the population is 16. So they're telling us, okay, you know what? We know the standard deviation of the population is 16. And so since we know the standard deviation of the population, we're going to be working with Z equals X bar minus mu sigma divided by the square root of n. And they're telling us that the mean is 266. And they want to know the probability of having an X bar of less than 260. So we're shading this way. So we want the probability that Z is less than 260 minus 266 over, they told us the standard deviation of the population is 16, divided by the square root of 60. Now, once again, I could be using the normal CDF, but I'm going to go ahead and go stats test Z test just because I think it's easier. Stats test Z test. And in this case, my mean was 266. My standard deviation was 16 days. My X bar was 260. N happened to be 60. And I end up getting a Z equal to negative 2.9. So we want the probability that Z is less than negative 2.9047, which equals 0.0018. So less than 1%. Very rare that it would be less than 260 days for an average. All right, not for an individual, but for the average. Now, the next thing they want us to do is the same thing, but the mean duration of these patients to be less than 260 if the standard deviation of the sample is 16. All right, so in this case, instead of looking at a Z distribution, we're going to do a T distribution. And this was for the normal. Well, we've already shown that they're going to have exactly the same graph. So this is going to be a mean of 266. This should be 260. And this is my X bar. And we're going to be using the T, which is T equals X bar minus mu S divided by the square root again. And the reason we're using the S is because of the standard deviation of the sample. Here we had the standard deviation of the population, but we don't now. So we want the probability that T is less than 260 minus 266 divided by 16 divided by the square root of 60. All right. So once again, I can do this by going to the stat test T test. So let's do that. So stat test T test. Standard deviation of 16. And then we go ahead and calculate. And we still get exactly the same T score because it's the same formula. So the probability that T is less than negative 2.9047 equals, but instead of 0.0018, we end up with 0.0025, right? So there's a little slightly different probability. It's a little more probable, but still fairly rare. Now, once again, I want to go into, so this would be our answer. And you can see that, hey, this is greater. And the reason why is there's more area in the tails with the T test. Now, one thing I want to go back and show you is, once again, we can go to second VARS. So I don't want you to forget that this exists. Second VARS, TCDF, negative infinity. And now we're going to go to negative 2.9047. Negative 2.9047. Our degrees of freedom was sample size 60 minus 1. So our degrees of freedom is always minus the sample size minus 1. And we're going to get about the same thing, about the same 0.0025. Okay? So the main thing is you have to use the T distribution if you're using the standard deviation of the sample. If you have the standard deviation of the sample, you must use the T distribution. Otherwise, the rules are essentially the same. The underlying distribution has to be normal, or the sample size has to be 30 or greater. All right, thank you.